Hi, welcome to the Coursera course on high-performance scientific computing. My name is Randy Levesque. I'm a professor here at the University of Washington in the Department of Applied Mathematics. And the course you'll be seeing is a course that I'm actually teaching this quarter. So most of the lectures you'll see will be recorded in front of a live audience. This is a course, Applied Mathematics 483-583, that's offered to both undergraduates and graduate students. And covers an introduction to scientific computing and a bit about high-performance computing. So I'll tell you a little bit today about what goes on in this course, some of the goals and the strategy for getting there, and also talk a little bit about what computer requirements and software requirements we have in order to experiment with these tools yourself, briefly overview the material, and then end with a brief demonstration and discussion of one particular example that will give you a flavor for the sort of things we'll be looking at in this class. So the term high-performance computing, or HPC, often refers to heavy-duty computing on supercomputers or clusters of computers, often with hundreds of thousands of cores or maybe millions of cores. In particular, here's a picture of Titan, which is currently ranked as the world's fastest computer by certain measures. This is a computer at the Oak Ridge National Laboratory in Tennessee. This computer has more than 500,000 cores. So the laptop I'm working on is a quad core. It has 4 cores, 4 processor units that can work independently. This machine has more than 500,000 cores and is capable of doing about 20 petaflops. So petaflops is a term we'll talk more about later, or flops in general. Flops corresponds to floating point operations per second. So the number of multiplications, additions, divisions, that sort of operation on floating point numbers, or real numbers basically, that can be computed in a single second. So petaflops refers to 10 to the 15th floating point operations per second. So the reason that this kind of computer is so massive and has so many cores is a result of the fact that we've really reached the limits of what a single processor can do. For many years, we've been following what's called Moore's Law, named after Gordon Moore, who worked for Intel. And back in the 1960s, he predicted that the speed of processors, or actually he was looking at the number of components on a chip, but related very closely to the speed of the processor, that would double every 18 months or so. And that held true for many decades, that engineers were able to pack more and more computing power on a single chip. The speed increased at a rate of about doubling every 18 months, which means over the course of 15 years, for example, that adds up to a factor of about 1,000. So it used to be that if you had a code that was running too slow and you wanted it to run faster, all you had to do was wait a couple of years and it would run at least twice as fast. That's no longer true. These days, if you want your code to run faster, you have to figure out how to use more than one core to work on the same problem simultaneously. So there's still something like Moore's Law that's in place now, called namely that the number of cores is roughly doubling every 18 months in current computers. So this graph here is showing 3 curves this is from a website called top500.org that gives a list of, every 6 months it's updated to a list of the top 500 fastest computers in the world according to one benchmark problem anyway. And the top line here is the total computing power of all 500 of these machines. And you can see it goes up. It looks like it's linear here, but this is on a logarithmic scale. You may not be able to read things here, but it's going from a gigaflop down here to a teraflop, which is 1,000 gigaflops, to a petaflop up here, which is 1,000 teraflops. So it's been increasing exponentially from 1983 to 2008. That's what's shown on this particular graph. That's the total computing power of the top 500 computers. If you just look at the number 1 computer on that list, that's the red curve in the middle here. It's a little more jumpy because one computer might be the top for a number of years before it gets overtaken by a larger one. But it's basically following the same trend. And even if you look at the slowest computer on this top 500 list, whatever is number 500, each 6 months, that's also increasing exponentially in terms of computing power. So in this class, our focus is more modest. We're not going to talk about massively parallel machines. There's some special techniques that one has to worry about in order to deal with massively parallel supercomputers. And you also need a very large budget if you're going to buy a computer like that or access to such a machine. So what we'll look at in this class is more essential things that will help you write faster code on your own laptop or on a small cluster that you might have access to. Some of the topics we'll cover are essentials if you do want to work on a supercomputer eventually. You need to know something about the languages that are used to do parallel computing, for example, which we'll talk about in this course. But we won't get into actually running things on supercomputers. Also, one feature of this course is that the focus is going to be on scientific computing. There's many different types of large-scale computing these days, but the problems that we'll focus on as sample problems will come from the field of scientific computing, which often means solving problems where we may be approximating the solution of a differential equation, solving large systems of linear equations arising in various applications, computing numerical approximations of integrals, numerical quadrature. That sort of problem is what we will focus on in this class.